We start section 2, mathematical description of systems, with the input-output description of a system, also called the external description of the system. It relates system inputs to system outputs. Knowledge of the internal structure is not presupposed. In this course we will work with multivariable systems, so we will assume that the system has m inputs and that it has p outputs. The inputs and outputs can be stacked into vectors. The input vector is u, and that's why it's in bold, and the output vector is y. So u is a vector in Rm and y is a vector in Rp. Here h is in bold because the system is multivariable, and h is an operator that maps u into y. Very often we'll simply write u, and sometimes we'll write u of t, because the variable u is a vector function that depends on time that evolves from minus infinity to infinity. A system is called static or memoryless if the output of the system at time t0 depends only on the input applied at that same time t0. This is the case, for example, for a network that involves only resistors. Of course, most systems of interest that will be tackled in this course have memory. Okay, we speak of dynamical systems. The output y at time t0 also depends on the input applied before time t0. A good example of a dynamical system is, for instance, an RC system. If an input defined on the interval t0 infinity is applied to the system, well, the output in that same interval is not uniquely determined. Different inputs before time t0 will produce a different output in the interval t0 infinity. So the input-output description lacks a unique relation. And this is why we need this relaxedness assumption. We need to assume that the system is at rest, to speak of input-output descriptions. A system is relaxed or at rest at time t0 when the output is excited solely and uniquely by the inputs after time t0. The system is relaxed or is at rest at time t0 if no energy is stored in that system at that same instant t0. Under the relaxedness assumption, it is legitimate to write y, the output, is h times u, where h is some operator that uniquely specifies the output y in terms of the input u. A relaxed system, or a system that is at rest, is said to be linear if the following relation holds for any inputs u1 and u2 and any real numbers alpha 1 and alpha 2. Otherwise, the system is said to be non-linear. A linear system satisfies the principle of superposition. So, for instance, if the input is u1 and the output is y1 through the system h, and if the input is u2 and the corresponding output is y2 through the same system h, well, any linear combination of the inputs, so alpha 1 u1 plus alpha 2 u2, should produce at the output the linear combinations of the output, so alpha 1 y1 plus alpha 2 y2. Well, let us take an example of the RC system. So we'll assume that the input is V of t and the output voltage is Vc of t. You've seen in previous courses that you can write the expression of Vc of t, and it is the following one. And the second term here comes from the initial conditions. So this is the zero state response, and this is the zero input response. You can see here that you cannot have linearity if the system is not at rest, because if you multiply the input by 2 and the initial condition here is non-zero, the output will not be multiplied by 2. So in order to speak of linearity, we need to assume that this second term is 0, so that the system is relaxed or at rest. A system is said to be causal or non-anticipatory if the output at time t does not depend on the input applied after time t. So the output at time t only depends on the input applied before and at time t. We say that the past affects the future, but not conversely. So if the system is relaxed and causal, its input-output relation can be written as follows. So the output at time t only depends on the input in the interval minus infinity t, and this is true for every t. Well, a system is time invariant or stationary if its characteristics do not change with time. And again, we'll have to make the assumption that the system is relaxed or that it is at rest. A system is said to be time invariant if the following relation holds, where d tau here is the delay or shift operator. And one way of rewriting this relation is to rewrite it as follows. So assume that we do an experiment today with the input signal u of t, and that we observe the output y of t. Then if we do the experiment at some other time, and this is, well, described by the fact that we use the shifted version of u of t, so u of t minus tau. So this might mean that, for instance, we do the experiment tomorrow. What we should observe is y of t minus tau, okay? And this will indeed be the case if the system is time invariant. In this course, we'll work with causal systems because all physical systems are causal, and we'll work with linear time invariant systems as we have described in the course of signals and systems. Well, you remember from the course of signals and systems that if the system is a linear time invariant, it is LTI, well, then you can describe the output by the following relation, okay, which is the convolution integral. So here y is the output, u is the input, and h is the impulse response. But remember, here we work in a multivariable framework, so u is in Rm, y is in Rp, u and y are vectors, so h here is a p times m matrix, so h is in R p times m. So it's the impulse response matrix of the system, and you can write it as follows. So h1 1 of t. The system has m input, so here we have h1m of t. Here we have hp1 of t, and here hpm of t. Okay, so this matrix, as I said, is in Rp times m. So for instance, hij of t, well, it's the output I. Okay, so output I when the input j is subjected to a Dirac impulse delta t. Okay, so that's the meaning of hij of t. And remember that if the system is LTI and causal, well, then the impulse response is causal. So h of t will be the zero matrix for t negative. If we go to the Laplace domain, things become simpler because the convolution integral in the time domain changes into an algebraic equation in the frequency domain. So we'll use the one-sided Laplace transform. And as I said, if you go to the Laplace domain, well, the relation transformed in the following one, where h of s here is the transfer matrix. Okay, it's the Laplace transform of the impulse response matrix. So here again it's a matrix, and this matrix is in Rp times m. Well, when the system is a single input, single output system, well, this transfer matrix reduces to the transfer function that you know, and it's simply the Laplace transform of y of t over the Laplace transform of u of t. And remember that we can speak of a transfer function under the implicit assumption that the system is relaxed at the time t is equal t0. The transfer matrix h of s is in Rp times m, and we can look at the entry hij of s. Okay, and that's the relation between the input j and the output I. So it's the Laplace transform of yi of t over the Laplace transform of uj of t. Okay, so this transfer function here, which is an entry of the transfer matrix, well, describes the relation between the input uj and the output yi. A rational transfer function h of s is said to be proper if the following quantity, and that's just another way to write limit when s tends to infinity of h of s. Okay, well, h of s is proper if this thing here is a finite constant. For instance, the following system, k, t lead s plus 1, t lag s plus 1, so it's a lead lag system, that's a proper transfer function. A rational transfer function is said to be strictly proper if this quantity is equal to 0. So for instance, the following transfer function, which is a transfer function of a first order system, is a strictly proper transfer function. And you have, of course, similar definitions for transfer matrices. P is said to be a pole of a proper rational transfer function if the following relation holds, and z is said to be a zero of the same proper transfer function when the following relation holds. So zeros and poles can be complex, but if they are, they come into complex conjugate pairs because we assume that the transfer function, which is rational, h of s, comes under the form of numerator and denominator polynomials with real coefficients. So in this slide we define the concept of a zero and a pole for a proper rational transfer function h of s, so for a single input, single output system. We will see further on in the course that you can generalize the concept of a pole to a multivariable system. The generalization of zeros for multivariable systems goes beyond the scope of this course. You have to consult the literature for that. So far we have talked about input-output descriptions that are familiar to you, and now I will start to introduce the state space description of a system, and for that we need the concept of a state. The state of the system at time t0 is all the information that you need together with the input from t0 onwards to uniquely determine the behavior of the system after time t0. So the state at time t0 summarizes the essential information about the past inputs up to time t0, which is needed in determining the future behavior of the system. So let us illustrate that using our favorite RC system. The input is V of t, the output is Vc of t, that's the voltage on the capacitor. Okay, so we would like to know the state of the system at time t equals t0, and what we know is the input, that's V here, the input voltage, well, from time t0 up to infinity. And the question is, can we uniquely determine the behavior, or what do we need to know to uniquely determine the behavior of the output, that is Vc, from t0 to infinity? Okay, and that is what we need to know, is the state of the system. And it's kind of obvious here that we need to know the voltage on the capacitor at time t is equal to t0. Okay, so the state of the RC system is simply the voltage on the capacitor. So let us take another example, an example from Newtonian mechanics. So we have here an object and we subject it to an external force F, okay, and we have a step-like input force, and we apply the force at time t is equal to t0, and we would like to know the motion after time t0. Okay, so we are interested in the position, let's call it p of t, and the velocity v of t after time t0. Okay, so the question is, what do we need to know to uniquely determine the motion of this object? Well, of course we need the position at time t0 and we need the velocity at time t0. So the set of two numbers, position and velocity at time t0, is called the state at time t0. Okay, and how the vehicle actually attained this particular position and velocity at time t0 is irrelevant in determining its motion after t0. The set of equations that describe the unique relation between input, output and state of the system is called a dynamical equation, and it's a state space description of the system. The state space description that you see over here is the state space description in its most general form for nonlinear systems and even time varying systems. So remember that u is the input vector, it's in Rm, y is the output vector, it's in Rp, and x is the state vector. Remember in the previous example that came from mechanics, we had that the state vector was composed of position and velocity, so it was in R2. Okay, so n was equal to 2 in this case. In the general case, x will be a vector with n components, n states, so x will be in Rn. Well, the state space description is composed of a dynamical equation. Okay, it's dynamical because here we have a derivative and it's called the state equation. It kind of characterizes the evolution of the state. Okay, and the derivative of the state is a function of the state itself, the input and time. So h here is a non-linear function. The second equation is a static equation and it's called the output equation. This is how the output is obtained from the state, the input and time, and again here we have here a nonlinear dependency. So remember that this state space description is for a system that is multivariable. So one other way to describe it is as follows, and here you can see the n state equations, right? And here you can see the p output equations, and remember that the functions over here h1 to hn are non-linear, and the functions g1 to gp are also non-linear in the general case. An item sign in red means that the relating information is for your information only. It's the same thing when you have a logo for your information, then it means that the whole slide is there for your information only. In the state space description that we've seen earlier, we assume of course that for any initial state xt0 and any given input u, the underlying dynamical state space equation has a unique solution. A sufficient condition for that is that the functions hi and their partial derivatives with respect to the states are continuous functions of time. If a solution exists, then the state variable x of t can be obtained from the initial condition in t0 and the input in between t0 and t. The state variable has dimension n, so the state variable lives in Rn, and the set of equations is called an n-dimensional dynamical equation. We speak of an n-dimensional state space description of the system. For a physical system, the number of state variables is equal to the number of independent energy storage elements in the system. So a possible choice of the state variables is to choose the variables that represent energy storage. In the following table you can find variables that can serve as state variables. Well, let us use an example from electricity. A capacitor stores potential energy and the relevant variable is voltage. So the voltage on a capacitor will often serve as a state variable. Another example comes from mechanics. Energy is stored, for instance, in the form of kinetic energy associated to a mass or an inertia element, and the associated variables, velocity and angular velocity, are often chosen as state variables. When the system is linear, h and j become linear functions of x, so x dot will be equal to this equation here, and y of t will be equal to this equation. Remember that this is the state equation, it's a dynamical equation, and this is the output equation, and this is a static equation. If a is a continuous function of t, well, this system will have a unique solution, right? You can see that there is still a dependency of time over here, so the system is time varying. We speak of a linear time varying dynamical equation or a linear time varying state space description of the system. If the system is linear and time invariant, the dynamical equations become as follows, and this is the state space description that we'll be using extensively in this course. Remember that x dot and x are in Rn, that u is in Rm. This means that there are m inputs, and y is in Rp. There are p outputs. Now it becomes very easy to see that A is in Rn times n, so A is a matrix with n rows and n columns. B has n rows, which corresponds to the number of states, and m columns, which corresponds to the number of inputs. C has p rows, p is the number of outputs, and n columns, n is the number of states, and D, well, has p rows, number of outputs, and m columns, and m is the number of inputs. Without loss of generality, because the system is time invariant, and well, if you shift the input, you shift the output, right? We can choose t0 to be 0, and that's what we'll do in the future. What we have here is the so-called state space description, and it consists of a first order, this is this equation here, first order matrix differential equation. You see that it is first order because it involves the first derivative of the state vector. This first equation is dynamical, and it's the state equation. The second equation is a static matrix equation. It's the output equation. The four matrices A, B, C, and D form a four-tuple, and this four-tuple is a realization of the system, and this realization is often represented as shown here on the screen, because you can easily see the dimension of each matrix. For instance, the matrix B has dimension n times m, so n rows and m columns. Remember the equations that are behind these four matrices. So we have x dot is equal to ax plus bu, y is cx plus du. So this is a dynamic equation, this is a static equation. A is called the state matrix because, well, it describes the evolution of the state. B is called the control matrix because it takes into account the influence of the input on the states. C is the output matrix, it relates the state to the output. And D is the direct feed-through matrix. It expresses the direct influence of the input on the output. Very often D is equal to the zero matrix. For a physical system, there is no direct instantaneous influence of the input U on the output Y. Well, the state space description can be represented as follows. Remember that the state equation is x dot is equal to ax, coming from here, plus bu, okay, and you go from x dot to x through integration, right? And the output equation is y is equal to cx plus du, right? So here we have the state equation, and this is the equation where you have the dynamics. You can see it here because of the integrator, and the output equation is shown here in the blue frame. Well, the matrix A models the dynamic relation between internal variables, and the eigenvalues of A will be the poles of the system. So this is how we extend the notion of a pole to a multivariable system. B models the effect of the inputs on the dynamic relation. C models the effect of the dynamic relation on the measured output variables. And as mentioned before, D models the direct feed-through between inputs and outputs. The so-called state space description is an internal description because we look at what happens internally inside the system. By looking at the states, we have an idea of what happens inside the system. Remember that the input-output description was an external description of the system. In this slide, we see that the state space representation is not unique. Okay, so let us take a matrix T, n by n, that is non-singular. This means that T is invertible. This means that T minus 1, the inverse of T, exists. And let us define a new state x bar that is constructed from the previous state as T minus 1 x. Okay, so obviously x is equal to Tx bar. Okay, so by taking derivatives on both sides here, we see that the derivative of x bar is equal to T minus 1 x dot, right? And now we can inject in here x dot is equal to ax plus bu. If we do this, we obtain this equation over here. And if we replace x by Tx bar, we obtain this equation here. So we have is equal to x bar dot. We can do something similar for the output equation. So y is equal to cx plus du. So we inject here x is equal to Tx bar, and we have a new output equation is equal to y. So we see that we obtain a new matrix, a new state matrix, a new control matrix, a new output matrix, and the feed-through matrix remains the same. Okay, so by choosing a matrix T that is non-singular, and this type of matrix will be called a similarity transformation, we can construct an infinite amount of realizations of the system. In this course, we'll construct control algorithms based on the description x dot is ax plus bu, y is cx plus du. Okay, but remember that this is the state space description of a linear system, whereas most physical systems are non-linear. Okay, so a linear state space description would be nice in order to describe such a non-linear system in an approximative way. And the idea to obtain a linear model from a non-linear one is called linearization. Okay, very often linear state space models are obtained through linearization, and the linearization procedure is based on the Taylor series expansion and on the knowledge of a nominal trajectory and nominal system inputs. Very often it will be based on a nominal point and a nominal system input, right? We have to, of course, remember that the control law that is based on these linear models, these linearized models, is only valid around these nominal trajectories. So suppose that the system is non-linear, and then we know that the general state space description for a non-linear system, here it's even a time varying non-linear system, is the one that we've given at the beginning of the course. Okay, and suppose that this non-linear system operates around a nominal state trajectory x bar, and that it is forced by a nominal input trajectory u bar. Okay, and we are interested in the behavior of this nonlinear system in the neighborhood of this nominal trajectory. So we are interested in x and u. X is in the neighborhood of x bar, so we write it as x bar plus some variation, and u is u bar plus some variation. Okay, so this is what we mean around a nominal state trajectory forced by a nominal input trajectory. Very often we'll be interested in nominal trajectories that reduce to a nominal point. Okay, so this will reduce to xt is equal to x0, something that is constant, plus some variation, and ut will be u0 plus some variation. Okay, in practice we'll be interested in variations around a nominal working point. So for system motion close to the nominal trajectory, we have the following equation. Remember that this is x of t, right? X of t, the state variable, is written as a perturbation around the nominal state trajectory. We have something similar for u of t. U of t is a perturbation around the nominal input trajectory, and of course this will be x dot of t. So we assume here that the perturbation dx of t and du of t are small quantities. So what we can do is write the Taylor series expansion. So what we'll do is take this equation and take the zero order term, that's simply forgetting about the small quantities dx and du, and this corresponds to this term over here, and this is of course equal to x bar dot of t. So this will cancel out with this one. So the second and the third term are the first order terms, and they involve the partial derivatives of h with respect to x here and with respect to u, and then we have of course the last term that involves, well, the second order terms, but this one we can neglect because we assume that dx and du are small quantities. So we are left with the terms that are over here, and this is a state space description of the variation. Okay, so we have the derivative of dx here, that is a function of dx and du, and it's a linear state space description, right? And well, we can kind of have a look at this quantity, partial derivative of h with respect to x, and if you look at it, well, it's a matrix. Remember that h is, well, a vector function, h1 of t up to hn of t, right? So this thing here is a matrix. It's the partial derivative of h1 with respect to dx1 up to the partial derivative of dh1 with respect to dxn, and here the last equation will be partial derivative of hn with respect to dx1, and here we'll have the partial derivative of dhn with respect to dxn. So you recognize the equation that we have found in the previous slide, and it's a linear state space description of the variation around the nominal trajectory. We had seen that this quantity here is a matrix, and we can call it A of t. Similarly, you can see that this is also a matrix, and we'll call it B of t to be consistent with earlier notation. So this is really a linear state space description of the variation around the nominal trajectory. What we have done for the state equation, we can do also for the output equation, and you would end up with this equation over here. What you see here is that, well, the matrices are time varying. This is because we work around a nominal trajectory, okay, and at each time, well, the state and the input are different, and this explains the fact that these matrices are here still time varying. But assume now that we work around a nominal point, okay, so this means that x of t is written as x0, okay, the nominal state, plus some variation dx of t. Similarly, the input is u0 plus some variation around that nominal input, right? So what would happen in here is that these quantities are replaced by x0 and u0, and you lose the time dependence, okay, and you have that of course for the other matrices. And now you arrive at a linear state space description, but it is also time invariant. Okay, so the matrices A, B, C, and D are time invariant, and you obtain a linear state space description around the nominal working point. So if you're working around the nominal working point x0, u0, you can obtain a state space description of the variation around this nominal working point, and this state space description is delta x dot is a delta x plus b delta u, and delta y is c delta x plus d delta u. It is very important to see that this delta u of t is the input u of t minus the nominal input, right? And of course you're interested in the state, not the variation around the nominal state. So x of t will simply be x of 0, the nominal state, plus the variation around that nominal state. Well, let us obtain a few expressions, state space expressions of some systems. We'll start with a very easy mass spring damper system that is shown on the screen, and we can write the equation of motion by simply writing, we assume here that x is this variable here, mass times acceleration, so mass times x double dot. There is the force of the spring, so minus kx, because it's acting in this direction here. You have something similar for the damping force, minus cx dot plus f. Okay, so you can rewrite this as x double dot is minus k over m minus c times x, of course, minus c over m x dot plus f over m. So what will be the state vector? Well, there is, of course, we need to take the variable x because the potential energy is equal to kx square over 2. Okay, so there is storage of potential energy, so we have to take the related variable, which is x, and we have to take x dot because we have kinetic energy that is stored, and it's mx dot squared over 2. Okay, so we have to take these two variables in the state vector, so I'll have to call the state vector x bar, and we'll say that it is x dot. Okay, so the state vector is in R2. There are two state vectors, so it's a second order system, which makes sense, right? So we have now to write the state space equation, and remember that it's written like this: x bar dot is a x bar plus b u. Okay, so let's do that. So x bar dot will be x dot x double dot, and we have to write it as a matrix A times x bar, right? And x bar, it's x and x dot, and then we have to write it as a function of the input, but the input will be f over here, so we have f, there's only one input, so b will be a column vector. Okay, so here we have x dot, well, we have x and x dot here, so we have a 0 over here and a 1 over here. Okay, so x dot is equal to x dot, and of course there is no influence of f. And for the second line here, we can use this equation over here, and we see that we have minus k over m times x minus c over m times x dot plus 1 over m times f. So this is my A matrix, and this is the B matrix, right? Well, what about the C and the D matrix? Well, that depends on what is measured. For instance, if we assume that only the position x is measured, then we have y is equal to 1, 0 x bar plus, well, d will be simply 0 here. So that's my C matrix, and this is my D matrix. Okay, so this is under the assumption that we x is measured. Okay, so this is then, remember that this is x dot, so we see here indeed that y is equal to x. Suppose that x and x dot are measured, then what we'll have, of course, is that y is, well, an identity matrix. The first line here will isolate x, and the second line here will isolate x dot, right? Plus, since we have now two variables that are measured, I need a vector over here, and what we'll have here is 0 and 0. This is the C matrix, and this is the D matrix. So for C and D, it all depends on what is measured on the system. So let us consider the example of a pendulum, an example that you've probably seen in other courses. The pendulum has a length L, and the, well, associated mass is m. Okay, so you can kind of see that this length over here is L theta, so the speed will be L theta dot, and the acceleration will be L theta double dot. So we can now write the equation of motion, mass times acceleration, ml theta dot, is equal to the force that is acting, and the force that is acting is this one over here. It's acting in the other direction, so we have a minus, and it's mg sine theta. We can cancel out the m and rewrite it in this form. So this is the well-known equation of a pendulum. It is, of course, a non-linear differential equation, so at some stage we'll have to do some linearization, right? So what we can do first is look at a non-linear state space description, right? So this means that we have to look at the state, and the state will be composed of theta, that's related to the potential energy, and to theta dot, right? And that's related, of course, to the kinetic energy. So, and this will be, of course, x1 of t, and this will be x2 of t. And the non-linear description, right, is simply x dot of t. So this is x1 dot, x2 dot is equal to, well, x1 dot is theta dot, so that's equal to x2 of t, And the second equation, x2 dot, that's theta double dot, well, that's minus g over L sine theta, and theta is the first state variable, so we have this thing over here, right? And this is h, the first relation is h1 of x1 x2, there is no input over here, and this is h2 of x1 x2. So this is the nonlinear state space description, and what we can do now is linearize around, well, x1 0, x2 0, that is in our case the origin, right? We linearize around theta is equal to 0 and theta dot is equal to 0. This means that we take x1t to be x1 0 plus a variation, and we do the same thing for the second variable. Okay, in this particular case, but it's only because we linearize around the origin, we have that x1 is dx1, so that's d theta, and in our case it's also equal to theta, and this one is dx2, it's d theta dot, and in our case it's theta dot, right? Again, this is because we linearize around the origin. Okay, so the linearized model will be dx1 dot, and then we have to take this one here, partial derivative with respect to x1 dx1 plus partial derivative with respect to dx2 times dx2, right? So this one will not give a contribution, this one is 1, so we have simply dx2. dx2 dot is partial derivative of h2 with respect to x1 times dx1 plus partial derivative of dh2 with respect to x2 times dx2. Okay, so h2 does not depend on x2, so this one will give a 0, and here we have to take the, well, remember also that we have to evaluate in the working point, right? So this one here, we take the partial derivative with respect to x1, so that will be minus g over L cosine evaluated in x1 0, so 0 times dx2, so that's not dx2, it's dx1, of course, so that's minus j over L dx1, right? So what we can do now is write the state space equation. That will now be the linear state space or equation, or the linearized state space equation, and this will depend on dx. So dx1 is equal to dx2, so we have 0 1 over here, and dx2 is minus gl dx1, so we have minus g over L over here and a 0 over here, right? So we know here from what we have got here, and this is simply because we have linearized around the origin, that you can rewrite this differently. Okay, so dx1 is theta, dx2 is theta dot, so we can also rewrite this as x dot, okay, which is theta dot here, theta double dot, okay, and this is dx1 dot, this is indeed theta 1 dot, etc., is equal to 0, 1 minus g over L 0 times theta dot, and this is x over here, right? Remember that this is only because we have linearized around the origin, and this we could have obtained, well, in a simpler fashion by simply looking at this equation here and writing, well, if theta is small, sine of theta is approximately theta, so we end up with this equation over here, theta double dot plus j over L, not sine now, times theta is equal to 0. This is the linearized equation, and again, if you take this state vector, you can rewrite it in this form. Okay, so for this example here, well, the second approach is again much faster, but of course if you want to go through the whole formalism, and this is what I wanted to do, well, it takes a bit more time, but of course you end up with the same result. In the previous example, we had linearized around the origin, but let us now assume that we want to linearize around the unstable position where the pendulum is standing upright. Okay, so x10 is then pi, and x20 is still 0. So we linearize around theta is equal to pi and theta dot is equal to 0. Okay, and we'll see that the situation is quite different. So in this case, x1 of t is x10 pi. Okay, this is x10 plus dx1 of t. Okay, so this is pi plus d theta. We have that dx1 of t is equal to d theta, but it's different to theta, right? And still we have x2 theta is x20, that's simply 0 plus dx2. So in this case we still have the relation that this is equal to theta dot and this is equal to d theta dot. So let us linearize around this working point, right? And we'll have dx1 dot, it's the partial derivative of h1 with respect to x1 evaluated at the working point times dx1 plus dh1 partial derivative with respect to x2 evaluated at the working point times dx2. This will not give a contribution because h1 does not depend on x1, and h1 it's simply x2, so this one will be 1 over here, so we have dx2. dx2 dot is partial derivative of dh2 with respect to x1 evaluated at the working point times dx1 plus the partial derivative of h2 with respect to x2 evaluated at the working point times dx2. h2 only depends on x1, so this will not give a contribution, so we have to take the partial derivative of h2 with respect to x1 minus j over L cosine, and now evaluate it at the working point. So x10 is pi here, so we have to write pi dx1. Okay, So this is -1, so this is j over L dx1. And now we end up with the following description, linear state space description of the system that has been linearized around this working point over here. So we have dx dot, that's dx1 dot, dx2 dot is 0, 1, j over L, 0, dx1, dx2. So this is dx over here. Okay, remember now that dx is dx1, that's d theta, that's the variation around pi here, and here we have still theta dot. Okay, so this is different to theta dot. If you're interested in theta, what you will have to do is take the working point pi and add d theta. This is very important, and this is now because we have, of course, linearized around a point that is different to the origin. Okay, so notice with respect to the previous linearized model that we have here a plus sign. Well, let us take another example, which is the LCL filter. It's a filter that is used in power electronics, and you'll encounter that filter in the teaching unit commande et interfaçage des systèmes électriques. There are two inputs, V in and V out, and we have to look at the states. Well, the states are related to the elements that can store energy. Well, you can store energy in the inductors, okay, and the energy will be L current squared divided by 2. So the related variable is the current. We have two inductors, so we have state variable EL1, the current through L1, and the current through L2, EL2. Well, you can also store energy in the capacitor, CV square over 2. The related variable is the voltage, so the third state will be here, the capacitor voltage VC. So what we'll have to do now is write the equations, okay? And, well, we have L1 EL1 dot, okay, that's this voltage over here, that's equal to V in minus VC, right? So what we can do is erase it over here and write L1 over here. We have, and it's very similar, EL2 dot, that's VC minus V out over L2, and we have that CVC dot, that's EL1 minus EL2. Okay, so this is the current that flows over here, right? And again, what we can do is put the C over here, and now we can write the state space equation. Okay, so what we'll do is write X dot, so we have EL1 dot, EL2 dot, and VC dot is equal to, and here we'll put X, okay, so that's EL1, EL2, and not EL3, of course, but capacitor voltage. Okay, so now we look at the first equation. Now we'll put also here the dependence on the two inputs. You have two inputs, so we'll have V in and V out. Okay, so by the look of it, A will be in R3 times 3 and B will be in R3 times 2. 3 states, 2 inputs. Right, so let us look at the first equation. As far as the states are concerned, it only depends on Vc, so we'll have 0, 0, minus 1 over L1, and it depends on V in, so we'll have 1 over L1, 0. Right? We can look at the second equation over here. Again, it only depends on the state Vc, so we have minus 1 over L2, and it depends on the output voltage. Okay, so we'll have 0 minus L2, right? And here it was a plus, right? And let us now look at the third equation. It does not depend on the inputs, so we have zeros over here, and it depends on, well, EL1 and EL2, so when we have 1 over C and minus 1 over C, it does not depend on Vc, right? So this is the state equation, right? So for instance, let us assume that only let us say EL1 is measured, then we'll have Y is EL1 and the C matrix we'll select the first element and we'll have 1, 0, 0. That's my C here. And as usual in a physical system, there is no feed through. So what we'll have here is 0, 0, and this is the D matrix. Well, let us make a small change in our system. You know that in reality, well, the inductor will not be perfect, so what there will be is a resistor here in a series, and we'll call it RL1, and similarly we'll have one over here and we'll call it RL2. So this means that the first equation will be L1 EL1 dot plus RL1 EL1, that's the voltage that is over here, right, is equal to V in minus Vc. So this means here that we have to adapt our equation. So we'll have this equation here and we'll have minus RL1 EL1 over L1, right? And we'll have something similar over here. We'll have to adapt our equation and we'll have minus RL2 EL2 over L2, right? So these are the two adaptations that we have made because of the two resistors that have been added. Okay, so what we need to do now is adapt our state space description, and there will be a change over here. Okay, so we'll have minus RL1 over L1, and there will be minus RL2 over L2. So we'll do another example, which is the two-tank system. This will yield a non-linear state space description and will linearize it around a working point. So the input is Q1, the flow to tank 1. There are two states, and the state is the height of each tank, so H1 and H2. So the section of the tanks is A, and tank 1 and tank 2 are connected by a connection pipe of section S, and the flow through this connection pipe is Q12. There is also a discharge pipe with the same section, and the discharge flow is Q20. So of course we would like to know Q12 and Q20, and from Bernoulli it's let's do it for this example here. We see that V12 squared divided by 2 is equal to H1 minus H2 times G. So this means that V12 is, well, the square root of 2G H1 minus H2, right? And Q12 is simply, well, V12, and you multiply by the section, and then you multiply by alpha, which is a discharge coefficient that is, well, somewhere in the neighborhood of 0 to 1, right? So this is Q12, and you can write it in full. It's alpha S square root of 2G H1 minus H2. And for this one you would have something similar. So Q20 is alpha S square root of 2G H2. So the first step is to write the equations and the nonlinear equations. So the variation of the volume, which is the section times the variation of the height, is equal to Q1, that's the flow that's coming in, minus the flow that is coming out. And we have just seen that Q12 can be written like this. And then we have a similar equation, and this equation of course was for the first tank. This second equation is for the second tank. The variation of volume, A times the variation of height of H2, is Q12, that's the flow that is entering, minus Q20, that's the discharge flow. And we have just seen that this is Q12 and this is the discharge flow. So what we have done here is take these two equations and divide by the section, and we end up with these two relations here, and they will form a nonlinear state space description of the two-tank system. And you can see that these equations are in the formalism that we have outlined previously. The variation of the state is a function H1 of the two states and the input. And remember that there are two states, H1 and H2, and an input Q1. Okay, so the variation of the first state is H1, a function of the state and the input. And we have something similar for the second equation. The variation of the second state is a function H2, that is a function of the state and the input. So what we'll do now is linearize the system around a nominal input flow Q1S. Okay, Well, for this nominal input flow, we assume that Q1 is constant and it is equal to Q1S. So there will be a corresponding steady state, a corresponding nominal height H1, which we'll call H1S, and a nominal height H2, which we'll call H2S. These can be computed quite easily because in steady state, of course, what comes in, Q1S, must correspond to what comes out, discharge flow, and must correspond also to what is flowing in between the two tanks. Okay, so this is Q12 at steady state when we have the nominal heights, and this is Q20S here, the discharge flow in steady state, and it depends on the nominal height H2S. Okay, so if we write that this is Q1S, okay, you square things, you divide by alpha S, then you square, you divide by 2G, and you obtain the corresponding nominal height H2S. And you can do something similar, it's not that difficult, and you will see that H1S is simply 2 times H2S. So what we can do now is linearize the system around this working point. So these were the two nonlinear state space equations that we have found previously, and they are in the format that we've introduced earlier on in the course, and now we are interested in the behavior around this working point. Okay, so which means that we'll consider Q1, H1, H2 that are variations around the nominal working point. For instance, H1 of t is the nominal height plus some variation dH1. And we've seen previously that you can obtain a state space description of these variations in the following fashion. So what you have to do is take H1, right, for this first equation, and then take the partial derivative with respect to H1, H2, the two states, and Q1, right? So let's do this, for instance, for this element here. So H1 is this relation, right? So if we take the partial derivative, what we'll have is minus, so this one will not contribute. We take the partial derivative with respect to H1, we'll have minus 1 over A alpha S square root of 2G. Then we have to take the derivative of this one here. So this will be a half 1 over the square root of H1 minus H2, and we have to evaluate this at the working point. So this will be H1S, H2S. You remember that H1S is 2 times H2S, so this will be here H2S. Oh, we have done this for this particular example, and you can do this for the other ones. For instance, for this one it's very simple because we have a linear relation. So if we take the partial derivative with respect to Q1, this one will be 1 over A. So we can rewrite this in the form of a first order state space matrix equation. Okay, and what we see here appearing is AL, the state matrix of the system that has been linearized around the nominal working point, and here BL. We have seen, we have computed it, that this one was 1 over A. This is what we see over here, and this one was, well, minus alpha S square root of 2G 1 over 2A 1 over the square root of H2S. s, right? So if k is defined as follows, we have minus k over here. This is what we have found in the previous slide. If you do the computations for these elements, and these elements, which is not that difficult, you will see that you have k over here, and minus 2k over here, and we have a 0 over here. So this is the state space description that allows you to compute the variations around the nominal working point, dH1, delta H1, and delta H2. So what I've done here is implement, well, the non-linear system and the linear system in MATLAB Simulink and compare the two so that we can have an idea of how good this linear model works around the nominal working point. Okay, so the M file over here, well, you have the variables A, S, J, and alpha, and I've given them, well, values. Here is the value of the input flow around which we are going to linearize. So it's 3 liters per minute. This has of course to be transformed in a Q1S, which is in cubic meters per second, and here is the computation of H1S, H2S, the nominal heights that correspond to this 3 liters per minute. Okay, so this is the k that we had computed, and this allows to construct the state space model linearized around Q1S, H1S, H2S, which is our nominal model. So we can now look at the Simulink model. Here you recognize the non-linear tank model, and here the linearization. And here we have an input. So what you have here at the input is, well, the input flow, okay, around its nominal value. So this is this 3 liters per minute, and what we'll do is do a variation around that and compare the non-linear model with the linearization. So this is indeed the non-linear tank. So these are the coefficients, and if we look below, these are the state space equations, the non-linear state space equations of the tank. Okay, you see here the two integrators because we have two states, and this is simply implementing these equations that are given in the slides, right? Here we have the linearization, and here we use a state space description. Okay, and what we use here are the matrices A, B, C, and D that have been computed and that are given here in the M file. Okay, so A, B, C, and D, right? It's very important when you use linearization that what this state space description sees is delta Q1. So what you have to do is take the input and remove the nominal input, right? And what will be produced at the output is delta H1 and delta H2. So we are of course interested in H1 and H2. So what we have to do is at the end add the nominal heights H1S and H2S. So we can now simulate the system. Remember, this is this 3 liters per minute, and what we'll do after 5 seconds is add something that is varying as a sinusoid, and the amplitude is quite large over here. You will see that the quality of the model stays quite okay. If we simulate the system, we can now have a look at the scope. Okay, so here below you see the input. So for 5 seconds it's equal to, well, the nominal working point, right? And then we start varying the input, and we can look here at the output of the nonlinear model and the linearized model. The nonlinear model is given in blue and the linearized model is given in green. Okay, so you can see that even though we end up far away from the input flow, the nominal input flow, the quality of the model stays quite good. So remember, these are the quantities that we, and this is the A that we obtain when we linearize around an input flow of 3 liters per minute. If we now change the value, for instance, to 5 liters per minute, well, of course, you will linearize around a new working point, so the model will be different, and you see that this is still corresponding what we had obtained by computation and what is generated by MATLAB Simulink. It is, of course, quite important that you, well, initialize the integrators that are in here with the correct values when you linearize the system. So it is also possible to obtain the matrices A and B symbolically using the MATLAB symbolic toolbox. For that you have to define all variables symbolically. So remember that X, the state is H1, H2, right? So the level in tank 1 and in tank 2, and X dot, well, it's H1 dot, H2 dot, and this is equal to, well, H1 of Q, H1, H2, right? And H2, Q1, H1, H2. So these expressions of H1 and H2 are given in the slides, and here they are. So in order to linearize the system, what you have to do, for instance, A11, you have to take this one over here and take the partial derivative with respect to H1, right? This is what is done over here. What is computed over here is the partial derivative of H1 with respect to the parameter H1, and then you have to evaluate in the working point, right? So you have to replace H1, H2 and Q1 by their respective values at the working point. This can easily be done in MATLAB using this symbolic toolbox. So this is how you obtain the matrix A, and you can do something similar to obtain the matrix B over here. There you have to take the partial derivative with respect to Q1, partial derivative of H1 with respect to Q1. This will give you B1, and if you take the second one with respect to Q1, you have B2. So once you have the expressions of A and B, the matrices A and B, they are symbolic. What you can do is replace the symbolic variables A, S, G, alpha and Q1S by parametric values, and this can be done using the command subs, and then you have to evaluate it using this command VPA, and this will give you the state space matrices A and B around the working point that is given over here, that corresponds to, well, 5 liters per minute for these values over here. So let us run this code and compute the linearization using the symbolic toolbox. So what you have over here is the symbolic expression of the state space matrices A and B. The expression of A looks a bit different, but here everything is done with respect to Q1S. So this is the input flow around the working point, right? In the simulations we had used previously 5 liters per minute. In the slides, well, the state space matrix is written as a function of H2S, but of course H2S is itself a function of Q1S. So these, well, expressions of the state space matrix are equivalent, and to see that, well, we can also have a look at what it looks like if you replace the variables by the expressions that we had used previously in the simulation. And you can see now that indeed this is really the expression of the state space matrix that we had obtained when we had done the linearization by hand and when we had done the linearization using LinMod. Well, you might wonder why it would be interesting to obtain a linearization of the system by hand. Well, here clearly you see that the realization is a function of the parameters. You can see here clearly that the parameter K depends on the section of the tank, the section of the pipe, and the discharge coefficient. So you can see how the dynamics evolve as a function of the parameters, and this can be interesting for system or process sizing, dimensionnement in French. Well, here is an example of such a mechanical system sizing in the case of the inverted pendulum on wheel, the two-wheeled robot, and this is really the one that has been constructed from scratch, not the Ediumip robot. So you can see here all parameters from the prototype, right? Calculation of some parameters, and here the state space model. It's a linearization around the unstable vertical position, and what you can see here is that there is a loop. So the A matrix is computed for different values of R, that is going from 3 centimeters to 30 centimeters, right? R here is the radius of the wheel, and what is done over here is that the main eigenvalue is computed, and this is done using this little function over here. It goes over the eigenvalues and it takes the maximum negative eigenvalue. So what you can then do is plot the value of the eigenvalue as a function of the radius of the wheel, and if you do this, this is what you obtain. And you can see clearly that the main eigenvalue is increasing with the radius of the wheel. This was important because during prototyping the wheel radius was chosen too small at first, and the dynamics were too fast, so fast that it was impossible to run the system on the Arduino system. So we needed a slower system, and this system simply showed that if you increased the radius of the wheel, well, you had a system that had a, well, slower dynamic, in the sense that the main eigenvalue, well, shifts to the right.